Okay, yeah, בואו נתחיל. Disclosure, this meetup will be in English. Hopefully everyone's going to be okay with that. And if not, we're going to upload the recording of the Meetup so you guys can rewind and take notes as much as you wish. So, first of all, let me introduce our community. We're a Web3 Devs underground community. We're a community of builders, Web3 builders. We started a community, actually Shauli Rejwan and Roy Sherov funded our community a few years ago. They started to notice this gap in the ecosystem here in Israel, where Web3 builders didn't really have a proper place to share knowledge and best practices and communicate their challenges building in Web3. 3 or 4 years ago, it still was a big challenge. Was very little forums or places to share or ask questions, and this is the gap that prompted them to start this community. Ever since, we've been hosting physical meetups where we try to gather everyone up, or as many of us as we can, once a month to share knowledge, give lectures, pure top-tier content, Web3 development, a lot of infrastructure, but basically we cover the whole scale of it. We try to. It's a good place to say that everything we do is for free, and we do to encourage other builders to come share the knowledge and basically help grow our community of Web3, of the global Web3 development community. So, without a lot of further ado, I would love to introduce our first speaker now. Nebo, can come on stage.
רגע, בוא תעמוד קרוב על המחשב ויש לי בעיקר המיקרופון. תעמוד באזור הזה.
Hi everybody. Hey. So I'm Nebo. I will talk to you about smart contracts in practice, and as you can partially see, I have the self-proclaimed title of making smart contracts dumber, which is what I'm going to try to convince you to do today. So why should you listen to me? I'm the application group manager at StarkWare. We have, so StarkWare is a firm that builds infra, right? We build Starknet, if you know what it is. If not, you can ask, I'll explain. But my group at StarkWare is focused on building applications, strategic applications on Starknet. And therefore, we have a lot of experience in building smart contracts and Web3 applications, and we try to be methodical about it. And I'll try to explain, to give you examples of how and why. So yeah, we try to be a consumer of our tech. That's part of the reason we build applications in-house. And as a group, the application group tries to be a mediator. Yeah. So the application group tries to be a mediator between the developers in the ecosystem to StarkWare who builds the tech. So you kind of see both worlds. So key projects we build are the Starknet staking infrastructure, Stargate, which is the canonical bridge between Ethereum and Starknet. We have perps dexes. We're involved in Lightning protocol and so forth. Yeah. Okay, so what I'll try to talk about is like the basic idea of what is a blockchain, the basics of how it works, so the storage and cost model of it, and how it affects building applications, immutability and visibility of the code and data, some good practices and real-life examples. And so I had a problem building this talk because I didn't know what's the levels of the crowd. So please try to ask questions. If you want to know stuff that aren't here, feel free to ask me. If you want me to talk about something else, I don't know, the privacy meta or DeFi or whatever, I'm pretty knowledgeable about crypto, so feel free to interrupt and ask me whatever. Just as a background, so before StarkWare, I'm in crypto since like 2015. I've been involved in lots of crypto stuff, so I have a track record. Okay, so what is a blockchain? I asked ChatGPT. He says a blockchain is a decentralized database that can store data and execute code deterministically. So let's unpack it. It's a database, right? So you can read and write data with a lot of caveats. We'll talk about it. It's decentralized, so it means that in order to be decentralized, your code has lots of copies, and the data that you store also is copied in each and every node on chain. Is it better now? Yeah.
רגע, אתה יכול לתת טיפה יותר לשם עכשיו, למצלמה? הנה המצלמה שלך, תשתגע.
אבל אני לא יכול לראות רגע. Okay, is it good now? Great. So, as I said, it's a database, so you can read and write data with lots of caveats. We'll try to talk about that. It's decentralized, so each code segment and the data of it is multiplied across all the nodes on chain. It has a lot of meanings. Everyone can see both the code and the data, right? No central control. That is, in the eyes of the developer, usually is a bad thing, right? In crypto and blockchain, it's really good, but in the eyes of the developer, it's challenging and it has side effects in a lot of stuff that you try to do. And it executes code. We'll try to talk about how, what are the limitations, and what are the risks of this ability to execute code in a decentralized database. Okay, so the storage model. Storage on chain is usually being stored in a key value pairs per contract. So when you build the application, you need to define what's the storage content that you'll write on chain, and you need to think about it when you try to design your storage model. I'll try to give more examples. This data is persistent, so whatever you store on chain will forever be there, and you should be very cautious of it, right? If I store something that's large and I would not need in the future, it has pretty low side effects for me, right? I'll pay for the transaction, I'll pay for whatever it costs to store this piece of data, it will forever be there. And as a network, it's really hard to price this in, right? when you design the network, you need to decide how much gas, which I'll talk about in a minute, you'll charge per write operation. And there is a big discrepancy between the actual cost of the data and the fact that it's going to be stored forever, and the cost for user operations, which involve this write. So there's like unwritten agreement between application developers and blockchain builders that you try to store whatever you need and nothing more. A practical example of how not to do it well is you build an NFT collection and you put all the JPEGs on chain. That's a pretty bad design, right? It's very common, but it's a bad design. Okay, so the cost on chain is described in gas units. Gas is the way we try to estimate the CPU cycles, so the computation required to run your transaction, and storage operations, so the writes and reads are ingrained into the CPU cycle. And there is a hierarchy of cost, which means that writing is pricier than reading, which is pricier than computation in memory. You should always have it in mind and try to design your algorithm to suit this cost model. Okay, so the constraints of immutability and visibility on chain. Once you deploy code, you can change it, right? And that's a side effect of the fact that data is persistent. And anyone can see the code and transaction that you send online. Basic idea is don't have bugs. We try to do a lot to make sure that you don't have bugs. And the idea or the methodology that we at StarkWare try to impose is we try to treat the smart contracts as hardware. That means that we try to write a simple code and try to offload whatever we can from the on-chain computation. We try to write a lot of tests, be very, very specific with the tests that we write, and try to make sure that we cover everything. And then we do multiple sessions of audits to basically whatever we do. We have internal audits with specialized participants for that. Then we do external audits with auditing firms. So we try to really, really make sure that whatever we put on chain is the minimum we need to make the application work, be secure, and not have any issues with the implementation that we put. Okay, so now let's try to talk about good practices. I'll try to come up with examples to the stuff I'm saying. Bear with me. Okay, so storage hygiene. As I said, blockchain is a database, but it's not really a database, right? Because the data is persistent, it multiplies a lot, and you need to be aware of how and what you store. Okay, so offload computation off chain. You should use events to keep track of events. And what this means is whatever operation you try to do, you should basically emit an event, always. That should be the default. The reason is that you usually don't know who's going to interact with your contract, and one of the powerful things of blockchain is the ability to integrate different applications to do new things. Very, very common in DeFi. So the more you try to prepare yourself to the option of somebody else will try to come with new ways to use your code, the better you'll be
going forward. So it's relevant both in terms of what API you expose. You should try to expose an API which will stay the same, show the state of the contract, and be meaningful to whoever is going to interact with it, assuming that you want to be a part of the deal. And you should emit events which will allow you to basically run off-chain operations that will compute whatever you want of this on-chain data. So if I try to wrap the two together, I would write some piece of code that computes something, writes the result of this computation on-chain. So that's the ground truth. If I want to read something, that's what it is. But I will try to store only the result and not the path to it or any intermediate result that I have. Events will help me to fill up the gap by notifying the off-chain component that something meaningful has happened, was computed, whatever, and I would be able to run the off-chain code to do further computation, keep track of things, and so on. Okay, another variant of what I just said is you do computation of off-chain and you verify on-chain. Like the standard way of building such an algorithms is using Merkle trees. But without going into what is a Merkle tree, I will try to say it this way. I have an application where I want to keep track of nodes, right? I don't care what is the content of these nodes, let's say WhatsApp. Okay, I don't care about the messages themselves. What I do care is that I want to have the smart contract managing this piece of information, make sure that the operations are valid, they have been created in an ordered way and in a way that I can, let's say, trust the loaded word. So the way I can do it is not store the messages on chain. I can store a representation of what these messages means, or the interaction of these messages on chain, and refer to it as long as I can, at the later process, derive the real data out of it. Okay, batch operations. So this is a nice one, I think, which is like looking at batch operations on chain is kind of a tricky thing. On one hand, if you really are in the like blockchain is my world, everything is decentralized, no central identity world, then you want users to sign on whatever they want to do, right? You don't want any operation to be happening without user consent. But on the other hand, we know from computer science that if we batch things, we can cache stuff, we can optimize them, and we can create a smaller footprint of our applications. And there are solutions for it. So one sort of these solutions is something that we implemented for one of the, so actually several of our perps exchanges. So purpose exchange, does everybody here know what is a purpose exchange? Or should I explain? Okay. So perpetual exchange is the most common DeFi tool in crypto. It's an exchange, so you can buy and sell stuff. And this stuff that you sell is a representation of an actual token that you would use. So let's say in a stock exchange, in a normal stock exchange, I have the way that the tool of futures or options. I would buy the right to buy an asset, stock, at a future date, at a future price. Perpetual is the same thing without a date. So I have the right to buy a certain token, Bitcoin, at a certain price, 110K, sometime in the future. This is what perpetual exchange allows you to do. And this is a very, very common use case for trading on-chain. Perpetual exchanges are very, very compute intensive. In order to match the trades of users, because everything is like for the future without a closing date, everything can live forever. You need a lot of magic to happen to match these trades. And Starknet or Starks is a good technology for that because it allows you to ingest a lot of computation into similar sized transactions. So Starks, StarkX, which was our original infrastructure that we sold, and was evolved to Starknet, which is a decentralized open chain. Uses Starks to turn operations into their own chain, and this trait of allowing to hold a lot of information, a lot of computation into transactions is very appealing to perpetual exchanges. I think currently 3 out of the 10 top perpetual exchanges run on Stark Tech. So it's pretty universal. Anyway, perpetual exchange consume a lot of computation to execute your transactions. How do we solve this issue? If we just send each user's transaction as usually you do on chain, the users will have to pay a lot of fees on their transaction, and the chain would be clogged because you have a lot of user operations that you need to serve, and you'll have latency because blockchain operations have inherent latency on the operations. So what did we do? We let the users sign on the trade that we're going to do. So the user wants to buy Bitcoin at 110K. He will send a transaction that he will sign, so it can't be changed to the operator of the exchange. The operator of the exchange can only decide what transaction to match this operation with. So somebody will need to agree to sell Bitcoin at 110K for it to happen. So the perpetual exchange operator will match these 2 transactions off-chain and will batch all these user operations into big chunks. Now, the operator has the operator can give the users the perception as if the transaction was immediately served, right? Because the operator can't modify the transaction. It can only fulfill it if it finds a good match for it. And if it does, it will give the user the appearance of an instant acceptance of this trade. Then the operator will batch these operations and will send transactions that hold lots of trades in them. What we then can do, first we obviously verify that the transaction was really signed by the user, and everything is legit, and the operator doesn't cheat, and everything, right, to make sure that we're good. And then we can apply smarter tactics to reduce the on-chain footprint. So for example, we would cache prices of repeating assets. So if everybody wants to trade Bitcoin, I can only take the Bitcoin price once, and I know it for everyone. It can, for example, cache the market maker transaction. So in general, most traders, when they want to buy something or sell something, the other side of the trade is some big entity with lots of money that is responsible for funding this operation. So we can take these market maker positions and cache them, and then we don't need to recompute them each time. Then what we only need to do is to iterate over each of these trades, look at the price that we took, look at the market maker position, verify that we do have a match on these positions, compute the risk factor, which means that we want to see that the user doesn't buy anything with money that he doesn't have, or wants to get himself into a position where he's going to be liquidated, where he don't have funds to finance his operation. And if everything is good, great, we store everything in one go. This rather long story is meant to describe you how you can look at the seemingly simple operation on chain, so match two trades, and find out that it gets really complicated really fast when you try to scale. And you need to be very mindful to how the users of the app that you're building would use it to see that you can actually serve the amount of interest you're planning to. By the way, we did the top perps exchange on Starknet called Extended. We're currently working pretty closely to that. We, it's hot of the oven. We last week did some optimization round for them and reduced like 60% of the gas cost for them. And we're trying to push towards 100 trades per second, which is a really, really high number. If you multiply it by how much trades you can operate in a day, it's like crazy numbers. So it comes to show you that if you do the right optimizations and you really are mindful in the way that you write these smart contracts, you can really scale it well. Okay, that's a really important one. Loops are an enemy in smart contracts. It's really hard to bound resources when you have loops which you don't know in advance the size of. Right? If you know that you have 10 values you need to iterate over, that's fine. But if you have a loop with dynamic length, that's like a big no-no in smart contracts design. That's just mind it. So test, I said it before. Unit test, a lot of unit tests. We do fork test, which means that a lot of times you have a code, you know how it operates when you do unit test of this piece of code. Maybe this smart contract is built from a group of smart contracts, so you do something like a test that combines all of them together. But how do you know that it will work on real data? what we do is we locally fork the network, and then we build our own blocks with real data from the blockchain, and see that it actually works with real data. One other kind of fork test that we do sometimes is we try to mirror the on-chain state. So we not only fork, but we send the mainnet transaction to this fork to simulate the ongoing state. And then we can operate on real live data, like live data delay. Testnet, so everything goes through testnet. That should be your default always. You'll be surprised, or maybe you won't be surprised, but like 90% of the applications developers that I talk to, and I talk to a lot, don't have testnet deployments, which is bad in two fronts. Once, you don't really get to test your code, and the other part is anyone else that tries to integrate with your code also suffers from it, because he'll have to test on mainnet. So if you build something, deploy it on testnet, even if you don't want to test it, which I advise you do, please deploy it on testnet. If you really want to be saint, then you also deploy on mainnet with mock. So a good example for it, for example, is currently we migrate on Starknet from bridged USDC. So we bridged USDC from Ethereum to Starknet, and we are transitioning into native minting of USDC. So basically what it means is that people can come to Circle, the issuer of USDC, with dollars, fiat. They can mint directly on Starknet this token, and you can use it on Starknet. And that requires us to convert each user's old USDC to USDC. Not that complicated, right? You have a contract, you have a bunch of new USDC on it. You tell the user, hey, come give me your old USDC, I'll give you the new USDC, everything is great. What we did is we deployed this logic on testnet and mainnet with new tokens that we invented that have no, that doesn't have any price, right? Doesn't have any value. And that allows everybody else that want to integrate with it, the wallets, the applications, whatever, to also do it and be prepared to the activation of this real token. So that's also an approach you can take. Okay, audits. What can I say about audit? It's an open question if audit worth anything. The amount of, you have Lotham there. Lotham, raise your hand. Lotham is our auditing guy. He's our security expert at StarkWare. He's pushing us to do audits. Audits basically, external audits is you go to a firm, you pay them a lot of money, they go over the code, they say it's shit, then you improve some stuff, and then they say it's mildly better, and we improve. Why does it worth anything? So, two aspects. One is this auditing firm, if they're good, usually have security experts that will look on your code and will find recurring issues. A good example for recurring issues is rounding errors, which is like the most common thing that makes DeFi applications crash. If you follow the recent balancer crash, the reason for that was miscomputation of rounding error. So somebody found a way to use a rounding error over and over again, and find a way to exploit it to take it to stealing funds. That's like the most common issue of smart contracts, because it's really hard to catch What we try to do to mitigate these kind of issues is we, on each and every piece of code that we write that has this potential rounding problem, we write two functions. One is called round up, and one is called round down. Then you can be a dumb programmer and decide that you, as a rule, want to, for example, round in favor of the user or against the user. And then you can just use this function without thinking about it and leave the auditing firm the job to make sure that you did the right rounding, but at least you'll know that you're consistent. What a lot of apps is doing, instead of doing this, is just rounding whatever it works for them in each place in the code, and you have tens of rounding operations in your code, and nobody knows if you're rounding correctly or not. So that's one way to catch these kind of issues. I was talking about auditing. Okay, and the other common issue that audits usually catch is reentrancy. Reentrancy is basically, so since everything on chain can be a smart contract, when you call a function on somebody else's contract, you don't really know what this contract is going to do. And if by chance this contract is going to call back to you, this situation is called reentrancy, which means I started running my functions. It's basically a project, right? Start running my function, I called some piece of code, this piece of code called me back. And if you don't protect your function state from this scenario, it's a really common issue that will enable other actors to exploit your code. So that's also like a common issue that auditors usually catch. Also, you have someone to yell at and sue in case your code is really broken. Upgradability, I'm gonna talk about it in a minute, so I won't talk about it right now. Access control. Access control refers to who can do operations on this code that you write. When you have sensitive operations, so I created a new meme coin, and I have the mint function. Whoever can call this meme function can print these meme coins, which has lots of value, right? Because meme coins are great. And what I can do is condition this function that only my account can call this function. So only me can control the amount of minting of this meme coin. That's the basic access control description. And this is very important when you build complicated code. So you should try to make sure that you are mindful to the access of your sensitive functions. In practice, what we do at StarkWare is, first of all, we have a component that governs access control, and we reuse it all the time. So we did it once, we really checked it thoroughly, and we know that it works and it's safe and everything is okay. And we use it in a lot of our contracts, and we don't need to do for audits, so that's one. The other thing, to control, yes. Okay, modular versus monolithic architecture. So I didn't mention it at the beginning, but we said that writing data costs money, right? Costs gas, and we need to price it into whatever we do. This limitation is applied also to the pieces of code that you put on the chain. So there are limitations to the size of code that you can put into a contract. And once you start building complicated applications, you will soon hit this wall where you can't write your entire application into one contract. And then you need to shift into modular implementation, which means you have multiple contracts which work together into building your application. Now, this forces you to think of what you want to export and why when you build your code. So I think a good example I can give you is this perpetual exchange that I was talking about, for example. We know that computations of the trade matches is very computational heavy, and we want this part to be as cheap as possible. That's not a good part to move outside and have a separate contract for it, because you need to call the main contract, then you need to call another contract, and this costs money. So we put this logic into the main contract. But then all the access control, the ability of users to put funds into the contract, out of the contract, create identities, whatever you needed to do else in the contract, you don't have room for it in the contract size. So what we do is we wrap all each and every one of these categories of operations and move them into separate contracts and delegate the calls to the external contracts when we design this application. So we end up with one main contract, which is the point of entry to everybody, which has the most sensitive pieces of code. And surrounding it, we have lots of small contracts with each one a small implementation of some specific feature we want to add. Another approach of doing the same concept is the staking protocol, for example. In the staking protocol, we didn't have really the limitation of size, because it's a relatively simple idea, right? Staking means I lock money, I get a chance to build a block. When I build a block, I get rewards for this money that I put in, plus the block that I produced. So the staking protocol has some very sensitive pieces of code, have some sensitive pieces of code that we didn't want to have in the main contract. So what we did is took the parts of the code that we thought are sensitive. We want to make sure it has special limitations on them. For example, they can't be upgraded. They have special access control to them, and we export them to separate contracts. And we put the main logic into this contract. So that's another case of choosing modularity, but for different reasons, right? For security reasons and not size or price reasons.
I want to ask what you said, you have like one monolithic contract that calls multiple different contracts that have different features. And so this is talking about PVM contracts, right?
Not necessarily, but sure.
But you have like an API code trailer to the monolithic contract that specifies which function to call. How does it know like which feature to select?
How to map the default calls in VDM?
You have a call to that monolithic contract with some function signature, some kind of related function which action you want to do, and that contract has access to multiple feature contracts. standard, how does it know to mark which feature? Like, how does it know what are the features?
Okay, so the question was, if you have one monolith and you have multiple different contracts surrounding it, and each one implements some piece of the API, and you get a call to a piece of an API that is not part of the monolith contract, how do you know which one to call? Okay. There are two approaches to it. One is you don't do a star design. So you have the monolith, then you have layers. So you have a contract which has some of the API, and it is also delegating some other part of the API. So if you get a call, if it's not part of the main contract, and it's not a part of the secondary contract, it will be part of the third one. So that's an option. Another option is to actually have the API on the main contract. So not use the default call to delegate automatically. You can delegate explicitly. Okay. Done? How much time? כמה זמן? Okay. After I touched about it before. Okay, so I have here a few slides about how to approach upgrading on EVM contracts. It will take 10 minutes to explain. It's okay. Last 5. The whole world. Okay, so quickly, how does upgrades on EVM chain works? Basically, okay. You have a proxy contract which doesn't hold logic. It only holds storage, and the code you write sits on a logic contract, which the calls are delegated into. This pattern, called the proxy pattern, allows you to switch this logic without touching this part of the code, which you can change. Right? The issue is you run into storage collisions, which is a case that is described down here, when the main contract defines two storage components, which consume slot 0 and 1, and the proxy contract also has storage, and it's on the same slots. So how do you prevent this kind of things from happening? I'll give you a few suggestions. One is reserved slots. Reserved slots is, I define a constant. It's a hash of something, usually the name of whatever I reserve. And I explicitly write and read from this specific location. The way Ethereum assigns storage is by index. So you start counting by the order of the storage slots that you've written. So one approach is specifying specific hashes you want to write and read from. Another option, which I prefer, is using a storage gap. Storage gap means you write your code, and at the beginning you don't know how many storage elements you'll have in the future. So you just save a gap in advance. You save 50 slots worth of data that hold nothing at the beginning. And then on each upgrade, you reduce this part based on the new items you add to the storage. So I added one item, and then I reduced the slot size. And that way, I can make sure that although I don't know at the beginning how much data I will need, I will have space for it, assuming I will hit 50. And I won't need to do this shenanigans with the hashes. So that's a nice approach also. Okay, I want to talk about inheritance. Just mention that on Starknet, we figure out a different way to implement this thing. So we have two features that not have these issues. One is we have replaceability by design. That means that each and every contract can keep its address, but replace its class hash, which is the representation of the code. And then you are able to upgrade the contract without touching the storage, but just replacing the code that runs on it. And the variables on Starknet are addressable by hash of the name. So instead of doing 0, 1, 2, 3 on the order of the components of the storage, we hash the name of the component, and then we don't have this kind of collisions. If you upgrade to have different name, it will go to a different location. Yeah. Okay. That's it. Thank you.
Okay, thank you very much for this amazing
Okay, everyone, let's all grab a seat. Let's all grab a seat. We wanna start our second session. Okay, so for our second session, I would like to introduce Michael Sutton. He's the co-founder of Caspa protocol, and he will be here to discuss some very interesting topics. One moment. Meanwhile, you guys can grab a seat. Michael, whenever you're ready.
Hi everyone, nice seeing you all here and abroad. My name is Michael Sutton. I'm going to speak about vProgs, which is a new specification suggested for implementation over Caspa. Yeah, a few words about myself. I have a master's in computer science from the Hebrew University, HPC Power Computing. I joined the Caspa effort through the founding DAG labs. Mostly did research with Jonathan Sokolinski in the first years. So pre-mainnet, which is pre-2021, I mostly did research on Caspa. Eventually, a paper which came out of that effort is called DAG Night. Post-mainnet, I was a big part of the actual development in Caspa. I was part of leading the Rust rewrite effort, which eventually led to where Caspa is today, crescendo with 10 bps, so 10 blocks per second on mainnet, a high throughput L1. And this effort is about bringing programmability to Caspa as native as it gets. And it's a complex topic, spanning like a year and a half of brainstorming and thinking, so I'm obviously not going to cover the whole thing. I'll barely touch on some subsets of this thought process and the outcome, and I'll do my best to present it in a way that gives each one of you something out of this talk. So that's the overview. So to give you like a framing of my talk, I'm going to try and explain the special attributes Caspa L1 has, which is pretty well known, high throughput and very high frequency, speed. And through that, and also, present the obvious design goals, what you want to have from your programmability layer. And that should lead us into the way of thinking of how to design programmability over Caspa in a way that utilizes the better foundation, the more modern foundation Caspa provides, high throughput L1, but utilize it as well as software related, as well as ZK technology, which made tremendous progress in the recent years and is much more ready for actual usage and scalability of the system. So in terms of L1 foundations, Caspa is already scalable in the L1, meaning it can compute and have data throughput of currently, as of today, 3,000 transactions per second in real time. So Caspa L1 provides the data throughput of a lot of TPS at high frequency. However, we still want to keep it thin in terms of we want to add programmability to Caspa, but we want Caspa L1 to focus on being proof of work, Satoshi inspired verification layer, another computational layer, which means a lot of on-chain computations and complex state, etc. So the design goal is to have to use Caspa's throughput as a sequencer, but not necessarily have native smart contracts which actually execute on chain. So we have the privilege of designing over a new L1 and learning from a lot of the experience gathered by the industry and a lot of the progress made. So that's a very critical point as well. So what do you want from a programmability layer? So of course you want, so as I said, keep L1 verification focus, which is important for this decentralization. You want L1 nodes to remain affordable and commodity hardware. You don't want to make the threshold for entry for hardware on an L1 node. We don't want to increase it. So that's one main motivation for keeping it verification focused. What do you want from the programmability layer otherwise? So if possible, it should still have the user experience and the developer experience that a unified blockchain has. You want developers to compose programs with each other, to use smart contracts, to call other smart contracts. You want compatibility, and you want a unified liquidity space in terms of the economy. Another goal I could state you would want is that we don't necessarily turn into a system where there's one fat L2 that everyone needs to execute in order to maintain state. It doesn't make sense to have this keep just shifting all the execution of smart contracts, just shifting them from L1 to L2 doesn't make a lot of sense. You still want to keep apps independent of each other as much as possible. So the beginning of this path, it became obvious that we want to narrow down. I'd say from the terminology in the Ethereum world, we want to narrow down to one specific type of rollup zero-knowledge-based solutions, which are based rollups. Because the L1 is already providing the data throughput. So L1 can actually sequence and provide data availability for a lot of transactions per second. And we only want to shift the computational cost and the state size of complex state away from L1. So this brings us to the area that is called based rollup. So based rollup is a type of rollup that is based on the sequencing of the L1 and the data availability. So completely, the user actually submits transactions to the L1. You can also have a proxy, but he always has the sovereignty and ability to actually send the transaction directly to L1. And the rollup is obligated to execute that transaction. So the sequencing and the censorship resistance and the security of the transaction is actually provided by the L1, and the L2 is only interpreting the state according to the sequence provided by the L1. So it, in a sense, inherits the security and decentralization guarantees of the L1. So I'd say we're in this area of the design space. We want to focus on base sequencing, and then zoom in further and understand what other properties we want. So if we just go into the root of a base rollup, you still find yourself in a tension, in some tension, because either there's one very strong L2 rollup, which repeats the monolithic problem I described before. It's still one big system, still processing 3,000 computational transactions. If anyone wants to keep track of the state of a specific program or contract that actually needs to execute many other programs, possibly, every app doesn't depend on its own usage, but is suffering from the noisy neighbor, you would say. If another app has much higher frequency and they still compose, so also the low frequency app still needs to execute all the transactions, but the other app in order to keep track of the state. So one single L2 isn't a good solution enough in our eyes. So on the other hand, if you say, okay, let's have multiple L2s. Let's have multiple rollup entities, all using this L1. What you usually suffer from is the inability to compose transactions between L2s. So you get things, terms known as liquidity fragmentation, etc. So an application cannot freely compose with any other app in the space. It can only freely compose with applications in its own L2. So it kind of creates a two-dimensional mechanism design constraint. The apps are not free to communicate with each other and in the whole space, and they're kind of tied to their subgroup, which isn't healthy for the economy and has many side effects. So why, when we focus on base sequencing, can be said that we have an opportunity, which doesn't necessarily exist by any base rollup and other systems. So the fact that the L1 is a single sequencer for a lot, assume, okay, let's take the base rollup idea and let's assume we have 10 for now, or 20 base rollups, each grouped by some kind of logic or VM or whatever. So as these rollups, we have a unique design opportunity. The design opportunity is because they are all sequenced by the same sequencer. So if you think about it, there are multiple transactions aimed at each rollup, all sequenced by the L1, in one canonical order globally. That means that at the time of execution of a single transaction, there's actually it's scheduled to have one slot. The state of all other rollups is also deterministically known at that moment because they're all looking at the same L1 sequence. So if you look at the same L1 sequence, you can get to the same exact deterministic state. And this means we can consider or even dream about synchronous compatibility between all applications. Even though they're so-called executed each within a sovereign rollup, they can still conceptually communicate with each other synchronously because they all agree on the exact same sequence of events. So they agree conceptually on the same state. That means that essentially it's still, if you allow sync composability, essentially still solving a single consensus, single state machine problem. So it isn't just a neat property. I can simply compose with other applications. It's a very fundamental attribute of a system. However, this introduces a challenge. There's an obvious tension between achieving the two. Because if an application wants sovereignty, if it wants to be you have an autonomy about its resources. What happens when it wants to compose, or when someone else wants to compose with you? How can you compute the state driven by the other party in the mutual computation? There's an obvious tension between how autonomous I can be and the ability to compose with others. And I would say that there must be some kind of compromise. Like, you cannot treat the other rollup as not knowing about technology stack, how to run it. If you don't know enough, some information about it, there's no way you can compose without trusting, some way or another. There's one exception, I'll get to it, unrealistic exception. So there's an obvious tension here. So between this desire for sovereignty and the desire for composability. So I'm going to present an architecture which utilizes this Caspa shared sequencing to allow sync composability while still giving sovereignty and resources of each app. And in a sense, I'm going to tell you the end. In a sense, once you enable each app to compose with the others, you can essentially start calling it a rollup. Like I mentioned before, 20 rollups. You can zoom in and just create micro rollups or applications, because the whole reason for grouping applications into a rollup was to have more native, the native ability to speak with one another. And if the system allows everyone to compose, it kind of flattens the space, the program space, to a one-dimensional space. And there's no need for artificial grouping. You can obviously have grouping by attributes. You can have grouping by the same VM running, or the same prover system, or whatever. But there's no need to, the composability doesn't define borders anymore. I'd say that's the best definition. So the designers will get shortly to some illustrations. It's not going to stay all text. I first want to explain, okay, I'll focus on the first point first. So the design is based on logic state separation, meaning programs, we call them programs, inspired in a sense from Solana, because it just so happens that we need these dependencies declared in order for us to make it even possible to design such a system. So there's a state logic separation. A program is stateless, unlike the other smart contracts described before in some sense. Obviously, a program still owns accounts, and some of the accounts are used for managing its state. So they're more frequently read and written. But there's a strict separation between the logic, the program, and a set of accounts which the program will own. And transaction issuers are going to explicitly state their dependencies. At runtime, they might not use all dependencies, but they cannot access anything out of these dependencies, and they cannot write anything not declared as written.
So I want to ask a question about, you said so a program, a vProg is a stateless program, but it maintains ownership over the things like the account state. So where is that state stored?
We'll get to that.
Okay.
If I don't remind me again, but essentially an L2 node can choose to be stateful in some vProg, and then he'll have the full state. But if he wants to create a transaction which composes his prog with another, there's going to be data sharing on L1 in order for the other party to be able to trustlessly compute.
The vProg doesn't have to deny like having access to the other.
No. Okay, I want to touch on the third point, which is solving on-time execution. So if you think about it, if you want to compose with others, you don't necessarily know their state trustlessly. So there's one option if we had real-time, actually real-time proving. So assume this composable transaction where there's one program executing and then there's a remote call to another, a CPI call to another program. So imagine a world without latency and real-time moving. I can trustlessly ask the other party, okay, send me a ZK proof of your side of the execution, and I'll take the result, and I don't need to execute it. So in that case, if that would be possible, it would be an actual black box. I don't need to execute, and I don't need to trust. Obviously, that's not possible, probably not going to be possible, because even if you had ZK proofs immediately, it's still the communication cost within composable transaction will be the limiting factor, will be the bottleneck. So this drove us exactly to that on-site execution. We're saying, okay, we want to provide just enough information for the composable transaction executing so that all parties can execute all parts of the code by all the programs through a mechanism verified on L1. And that seems that like any other option would require some kind of trust. Like I can trust you until the proof arrives, but then I start proving a dependent execution based on your promise, which is already like a different realm of problem we prefer not to get into. So our design goal is to pay the price in terms of more data on L1 in order to avoid this dependency, in order to provide the real sovereignty of execution, which which inherently also means you have sovereignty about proving in worst case scenarios. Because if you can execute, you can also prove. Okay, so computational DAG is a very well-known topic from where I come from, computing. Any computation you run on your computer, any program running, can be described as a computational DAG, which describes the data flow. I can write an algorithm which solves the same problem in two different ways. One way I show you that the dependency DAG, the computational DAG, is very linear and all sequential, meaning there's no parallelism enabled the way it was written. And other code can be inherently, I can show you the data flow isn't sequential and is more parallel enabling. So computational DAG is a very usually not explicitly maintained construct, which represents the flow of a computation, and it helps analyzing very interesting stuff, including like how much can a program be parallelized, for instance. And there's more interesting theoretical use cases. In our case, we want to actually explicitly maintain the computational DAG on L1 for two purposes, which we'll get to. But first, just the basic modeling. What do we mean by a dependency, by the computational DAG, the CD? So transaction services, so L1 provides some kind of sequence of transactions, X1, X2, etc. And the subscript 1 is going to be like the time. Transaction time would be to deterministically indicate a specific transaction in the sequence. So transaction services would be in a triangle. Account state services represent the state of account at time t. So in this case, you have transaction x1 reading the state of account A and writing to the same account something else. So A is both a read and a write. So that's the little DAG we see on the right. If we take this a little further, so we have a sequence of a few transactions, x1 from A to A. So I'm mostly in this presentation, when I say account A, I mostly just assume that account A is also vogue A, and it only has one single account for simplicity. How long do I have?
20 minutes.
Okay, so there's no one after me. So this is a simple one. X2 is B to B again, X3 is B to B again. If the sequence would be different, it would still be looking the same, but the data flow might be different if the sequence changes. and the idea of these vertices would be different as well. So obviously different CD. X4 is a composable transaction. It's a simple type of composition, meaning it's only executed by prog A, because only A is being written to, kind of assuming that you don't read through someone else for computational reasons. If you call someone else, it obviously also writes something it needs to. So A is only one executed, but this is like a simple type of composition where the transaction X4 still reads from the state of B. A multi-writer composition would be a transaction which actually contains CPI remote calls and is just a generalization of this. It's doesn't add significant complexity to the conceptual design. Obviously, implementation-wise, that's where a lot of the heavy lifting is. But I'm actually not touching that.
So, giving the example with X4, the program that like A has, before sending the transaction, you need the state from B before, no? Like,
yeah.
Is that like the responsibility of like the vProgs?
So we'll get there in a second. You'll see what witness anchor sharing means. But that's a great question. When I say that L1 maintains the CD, it's a meta data structure. It's not actually maintaining, obviously, the data that's going to flow in all these vertices, but it is keeping in mind which prog knows about which vertex, account state vertex. So it's keeping track of how stateful the stateful vertices for each vProg, and I'll show you soon why we do that. So this is a basic structure. Okay, transaction scopes. So assume we had a ZK proof at time 0 at the bottom, which is submitted to L1 as some root of a program B, which is proven to be executed up to time 0. So the issue of transaction X4 in this case is actually going to include a witness to the state of B at time 0. And this witness is going to point at time 0, and L1 can verify that witness. From there, that means essentially that A, in order to execute X4, is going to need to execute both X2 and X3, because it's getting the witness 3 times back, so it's going to execute X2 and X3. So the computational scope for prog A for transaction X4 is this shape. And L1 is actually going to calculate the cost of this transaction to A and regulate for each prog according to some predefined parameter how much computations it's going to need to have. So that's the main, or the first main ingredient as to how we provide execution or computational cost sovereignty for each application, because L1 can actually track the cost. Yeah, so, I just mentioned that the algorithm for computing the computational scope for each transaction is relatively simple. It can be illustrated here. If you go back to the reset of the transaction X4, which is A1, B3, and you go back until you reach, you do a backwards PFS traversal until you reach either some stateful vertex, which A already knows about, or an anchor provided by a witness. Easy enough to figure out your going out of or overflowing, and then you would just help. But that's the basic algorithm. So the second main role of the CD is to be the skeleton or the guideline, the guide map on how to prove transactions in the most limited sense possible. So if you think about it, so for that, we need to actually stop maintaining the CD only as a data structure at L1. We actually have to hash it. And we need to keep it as a hashable structure. And that's for, I don't know if I need to give an intro for ZK, but ZK proofs and verification require a succinct parameter that can use and expand by private witness data. So we have to have L1 kind of compress this information encoded in the CD so that proofs can use it in order to compose or to prove they composed a complex interaction correctly. So here, there will be a two-stage. So in order to understand why it must be a two-phase solution, think about it. If this wouldn't be BR, this would be C. So we had a puzzle of multiple programs composing with each other. So obviously, so everyone involved is going to execute all vertices they need and know exactly what data is going to flow. But you don't want everyone to prove everyone else. So that's where you need a two-phase solution. You need some kind of batch submission to L1 of conditional statements. Okay, I can send, before going into the batch, so I can send a proof that condition that some, assuming the input of B is such and such, running program B or B would result a write to be such and such. So I can prove a single vertex conditional statements, and then submit them to L1 as a batch of conditional statements, and then everyone can use the proof submitted by other parties, and they're not going to need to ZK verify the other proofs. They're going to rely on L1 for verification. So you only need to implement ZK verify for your vProg infrastructure on L1, but you're actually going to see on chain a batch of conditional small proofs, which are succinctly in one submutable, and then you can provide it to the second phase, which is only the stitching based on the CD commitment. So the CD is going to help you show, okay, these are all conditional small proofs, and the CD shows me how to connect them to each other and see that the output of the previous one actually matches the conditional input of the next one. So if everything matches according to the CD as a guide map, you get a complete proof for actual complete execution of the whole composable operation of many, many users. So that's in a nutshell, like how two-phase proof stitching. Okay, now I want to touch on something I find very significant in this design, and I'll try to explain. So my visual language here is that each column or vertical set of circles is just operations and a program A, B, C, D, E, G, E. So it's per program operations, one after the other. It's just the program operating within itself, within its own borders. And an arrow and a line, an edge, represents like an unusual event, a composition event between two programs. So here I'm neglecting like the directions of the dependency of the composition, and just focusing on just this event of a composition. On the side, that should be an F representing frequency. So I'm saying, okay, let's assume there's a system with this just n votes, and there's a random composition between two votes in random according to some sample rate. Like in this drawing, you say, okay, there's a composition every so-called round or something. And the green thing represents like the length of proof epoch, like how long between proofs. And also assuming for simplicity that there's one synchronized point in time every F steps where everyone submits a proof for everything that happened before. So let's try and analyze what happens to the dependencies and costs over time. So obviously, if you take f, okay, think about it this way. Take f to a day. Okay, if a zk proof for the validity of the previous day is submitted every day. So the witnesses I showed in the previous slides can be only very far. They go back in time. So eventually, A is going to call B, B is going to call C, C is going to call D. Eventually, everyone is going to need to execute everyone else. It's going to eventually turn into, and it's all going to be regulated under the limits of each program. So it's going to converge into a single fat L2 in a sense. And if you take F to the infinity, and you can see it in this drawing where you go here and then here. So obviously, the A program needs to execute many other programs up until the most recent proof. And the way to look at it visually and also conceptually is to not stay in this complicated event space, let's say. But okay, let's create an undirected simple graph where each vertex represents a single vProg. And we draw an edge between two vertices. If within the F epoch, a composition event happened between these two progs. So what you'll see is this you get, in this case where F is large enough, you get in this random graph a giant component, exactly representing all these dependencies forming into one entanglement of complexity. However, if you start decreasing F and submitting proofs more frequently, the proof essentially compresses all the computational DAG and reduces all the dependencies. So now we're actually isolated in this area, and the only connections formed, all the previous connections are kind of already compressed into proofs and don't escalate. So when you look here, you can focus on this F epoch, and you see that there's no more large group of progs that have to execute each other, but actually they remain very small groups. And this is related to whoever wants to read about it. It's a phenomenon known in the world, in the theory of random graphs, the emergence of giant components. There's actually a threshold where if you sample below, it's a threshold for the probability of an edge in a random graph, where if you sample below it, the graph, it remains with very small components which are independent of each other with logarithmic size. And if you go above the threshold, it starts getting stitched together into a very large component. You can all imagine how it goes, but the result was surprising, and it's surprising intuitively because it clears a sharp threshold where slightly below it, all good, slightly above it, linear complexity. So what I'm trying to say here is that this kind of creates a system which is self-enforcing and encourages high frequency proofs, like submitting proofs more often and more rapidly, up to some equilibrium, I guess. It's still early to understand it fully, and obviously there's a cost. You cannot just submit a ZK proof every second. The constant in each proof. Okay, so a proof has a cost of producing, which is proportional to the length of the computation it's producing. So in that sense, there's no reason not to cut multiple proofs into one proof into multiple ones. But the constant cost of each proof is still significant, so you can't just say, okay, I'll prove each transaction on one year. There has to be some kind of constant factor. So it kind of creates a game where if you pay provers, or if you as an application kind of incentivize provers to create more proofs more frequently, the dependency graph reduces and composition becomes more cheap for users under the full implementation of this app. So more and more operations can happen, more and more fees, more and more proofs. So it's a flywheel of a mechanism design which should encourage both full frequency as well as not going into it, as well as parallelism as much as possible. The progs which will be designed with parallelism in mind will benefit much more from this architecture.
Can I have a question?
Yeah, sure.
Doesn't this situation though create kind of a game of chicken, like which vProg creates like brutal proofs? Because, for example, you said like proofs can incorporate, compress within them like the state from other nodes. So maybe if I wait for some vProg to like rely on some a very like a set of other vProgs state, I can like wait until they produce the proof to rely on that. Do you get what I'm saying?
Not necessarily, but there's obviously
Like that other people, other vProgs submitting proofs will create a less complex
dependency.
DC for me.
Yeah.
So like maybe
I benefit from them.
I benefit from
But
them.
eventually, if I don't submit proofs fast enough, the composition with me is going to cost others. So it depends.
Not you.
So they're not going to compose with me.
Okay. So like
So I'm going to lose like usage.
you didn't like
If you stay like off, if you stop submitting proofs, the cost of composing with you becomes too large. Eventually, it crosses some threshold, and it's not possible anymore. But it's a good question because I think it highlights like there's a lot of, to me it's still, there's no formal analysis yet. It's obviously the intuition is strong here, but there is a lot of fine tuning and mechanisms you need to provide in order maybe to smooth dependency costs. There's all kinds of, if you go into the research post, you see a term called CAD, continuous account dependency. Maybe someone wants to declare in advance that it wants some org to track another account in order to not pay all one big cost when it needs to, but to do it rapidly. So that's kind of the final. This is the last slide. So, like I mentioned before, I see this as a design where we start from L1 speed and throughput, L1 sequencing, everything. So we can think about the throughput allows us to think about being all based. So everything happens on L1. Once everything is based, you can start thinking about composability, at least theoretically and also practically, as we're showing. And then once you have composability, you can go back to the rollups and shrink them in size and make them dApps or POGs. So that's the kind of trip we've been through. I hope you enjoyed the talk and the topic, and thank you for being here. Thank you
All right. Thank you very much, Michael. Thank you also to Nevo. I would like to take advantage of the couple last minutes to say thank you very much to our sponsors for this event, to StarkWare. They helped us make all this happen. Thank you very much. If anyone of you have any questions to the speakers or about the sessions or anything else you want, just feel free to reach out to us however you like, social media, face-to-face, whatever you want. Of course, follow us on all social media platforms and do a calendar for upcoming events. And that's it. Thank you all for watching and for coming. And see you all December 24th for our next physical event. And stay tuned for our online events also, which are going to take place a few days before. Thank you very much.
yeah.